talk about. This is based on some work that should be out maybe within the either this month or early next month. It's a work done with Tania Mandal who is a postdoc at ISR Bhopal. So, what I intended to do is to show you how to construct black hole solutions which are in basically in an environment. I mean, environment by means of environment of matter, like for example, it's in, maybe you can call it the environment of a matter, which also solves Einstein equation, and the matter is characterized by the matter stress tensor. So, in other, more concrete terms, I will be finding black hole solutions of Einstein equation with matter stress tensor, and these will be solutions which will be asymptoting to some solutions, far away from the black hole, to some solutions which are solutions of this equation again. There is a environment in which the black hole is sitting. The environment is created by this thing, and also the curvature that will be necessary to balance the stress tensor in that region of space time.
So this is a stress tensor with the back reaction. So this is not in the probe.
No, there is nothing probe. Yeah, I will be solving the full equation. Yes.
So such as a scalar condensate would be one example.
Yes. Yes. So why do I want to study this? So obviously I will be studying this in large D, but let me just tell why one should be interested in studying this. So I wanted to attempt a more complicated problem of understanding collapse of black holes, and to understand something called, these people have worked on something called critical collapse. If you can understand how what are the parameter regimes, initial conditions that on initial conditions in a GR problem that you can set, so that the system either collapses to form a black hole, or it doesn't. Since I will be working in situation where there is no cosmological constant, so the matter can just pass through and not do anything. So there is something called Chopwick critical collapse and scaling. So in that scenario, suppose hi. So I'm just telling the brief motivation of why anybody should be interested in doing this. So there is this problem of critical collapse of Chopwick scaling is there. So the point is that of the many initial degrees of freedom that you need to specify to set up your GR evolution problem, like some, as everybody knows, some three metric on a codimension 1 initial condition, initial conditions on those, some initial condition on the type of matter that collapses to form, and many other things. So the point of this is that choose any one of those initial conditions, and the Chopwick scaling simply says that the mass of the formed black hole is proportional to I'm telling you. So the thing is that choose any initial condition, and there will be a critical point of that initial condition, P star. So the point is that the black hole forms if P is greater than P star, and another point is this gamma doesn't depend on where what your initial condition was. It only depends on that which things you are fixing. Like for example, do you fix the some component of metric initially flowing in some direction, and the value of the metric doesn't matter, but this is something that point is that you can form smaller and smaller black holes as you approach this value of the initial conditions, and once you go below this, you don't form a black hole. This basically says that things just pass.
What is P?
Or P is any one of the parameters. Suppose say you start with the scalar, and suppose the initial velocity of the scalar. Suppose say suppose you are studying spherically symmetric scalar collapse. So initial velocity of that.
Any parameter
Yes, that's the point, that if whatever the tunable parameter that you have in your system, and near the critical point, it will be a plane of critical points, and then you can tune so that you reach near and near and form black holes of smaller and smaller mass. But yeah, the point is that this thing, whenever is studied, I mean, like modulo, this thing that you people did is mostly studied numerically in situations where like you have very specific situation, like you study scalar collapse or collapse of some weird like, or maybe axisymmetric collapse of photons or something like that, very specific, but also study numerically. But
Sorry, what do you mean by initial velocity of the scalar? You mean as shell, or what's the thing that you have in mind?
like, I mean, like you set the collapsing speed of the shell.
But you were talking about the scalar
Yeah.
field right here in which, oh, sorry. Yeah. Yeah.
Yeah. So a scalar is collapsing, and I'm just specifying the velocity of collapse of the shell.
I see.
You know, just more generally, the space of initial conditions is broken up into two parts. Those that form black holes and those that don't, as you know, right?
Yeah.
So, if you have any parameter that crosses that boundary, that's it.
Yeah. Yeah.
Like,
So this is a very easy parameter that you can tune.
yeah, I just wanted to know what's the, so here's, okay, so anyway, will you
Phi dot of
You know, no. The point is, this is just a, I mean, like a digression. I mean, like I will tell you.
I think
Yeah.
the nicest way to say it is the thickness of the thing.
Yeah.
You take a wave packet, the thickness compared to the Schwarzschild radius of the mass in that shell.
Yeah.
That's the most natural value. If that's big, won't belong in that group. That's fine. But then the details of the shape don't matter.
Doesn't matter. Yes, exactly.
Yes.
So the point is that I wanted to study this, but to study this, I needed to understand some more basic things. So what I was showing is use that, I mean, like what can be the end product of such a collapse if a black hole forms. Like it will be a black hole in an environment of the thing that it, I mean, like that collapse to form the black hole. So this is the aim. And now why large D? Because as I mean, most of you know that large D is a nice analytical tool to study like dynamics involving black holes, and I will be explaining how I am going to do this. So the point is that, I mean, like to start with, I mean before I going, so there are some caveats. So the caveats are that I will be studying solutions which are which have stress tensor which are of the order of D naught, or you can think of the order of 1, like they have order 1 strength, and so they will. So yeah, so this is the main thing, and I will tell you the rest of the details as I go on. So now point is before going to all these details, also let me just initial to start with just tell you what happened in when there was no stress tensor, like in general, like okay, suppose it was vacuum. I mean, so the point is to start. Since I will be constructing a black hole solution in a 1/d perturbation series. So to do that, I need to find one solution where I can start the perturbation series, like which is a good solution to start the perturbation series. And I say that the good solution is, say, like let's start with a static Schwarzschild black hole. So that's its metric is well known to everybody. In d dimension, it is omega square. So this is simple. So, but as you can know, I mean, like this static black hole metric can be written in various different coordinates. One particularly useful coordinate is something called, I wanted to preserve this, okay, something called a Schwarzschild metric. In which the metric of the black hole looks like something flat plus I mean some term which completely specifies the warping of the space-time caused by this metric. I mean, like it's flat plus something. So you can easily see in this coordinate system that if you move very far away from the surface R0, you reach the asymptotic flat part, and The good thing about this, like this coordinate can also be written in a more fancy way, as suppose you can say flat plus this is called O mu dx mu. This where psi is simply r by r naught and O is something n minus u, where n is dr and u is minus dt. So written in this way, you can also, I mean, like in some way, you can always see that Schwarzschild metric in any dimension can be thought of as dual to a membrane situated at psi equal to 1, and all the metric is simply, I mean, like what happens to the metric is simply determined by the distance from this membrane at psi equal to 1, embedded in a flat space time.
Sorry, what is psi?
Yeah, that's what I said. Psi is just r by r naught.
I normally read that as phi, but anyway.
Sorry, okay, wait, let me write it properly as psi. Is it one? Okay. Yeah. Okay. So you can always already start thinking of the static black hole as being dual to a membrane. Like the membrane is situated at psi equal to 1, and it is static because the velocity is in static coordinates. So it can be thought of as the membrane being embedded in flat space-time, and this is true in any dimensions. And the way it worked is because since it has no dynamics, so you can, I mean, like you don't need to take care of any other thing. So it works. So, but the point is that now you can do something more. I think I need to. Sorry, can I just? Yeah. So this is a work in progress. Please ask questions if you feel that something is not clear. So the point is that now what one can do is, I mean, like very well that this is a solution of Einstein equation. So what happens if we now, I mean, like take this metric and I mean, and convert, I mean, like I demand that this psi. Oh, by the way, this n can be thought of as like proportional to d psi, like it's a normal to the psi equal to constant surface. So what you can do is take the function psi and the u, which I defined to be very specific thing, and make them to be a order d to the power naught varying, like derivative functions of space time. Yes, I mean, like for now, yeah, that's why I said proportional to d psi. So you always have to construct it to be, I mean, like in this way, I have explicitly written it to be unit norm. I mean, every norm is comparing with respect to this metric, like this flat part only. Okay, so everything I will be converting this. The basic point is trying to convert this gravitational problem into a problem of something moving in this flat part. That's why it's useful to write it as something flat plus some extra piece. And yeah, so another important property. So this is what I want to do. I want to convert this psi and u as slowly varying functions of space-time. So you can think of that initially the membrane was, I mean, like there was some membrane which was at psi equal to 1. So now I am just making the membrane slightly undulating, and each locally each point is like this. So locally each point is like a Schwarzschild, and I am trying to patch together many Schwarzschild with varying parameters to construct the full dynamical solutions. And why I can do this? The point is that, I mean, like you can look at this metric and sorry. You can look at this metric and you can see that as like moving, like psi greater than 1 is actually moving away from the horizon, as you can see from the definition of psi. So as you move away from the horizon at r naught, the value of psi increases beyond 1. So as you move away, I mean, if you have really moved away very far, I mean, like if psi minus 1 is of the order of 1, and if d goes to infinity, you can clearly see that this part just vanishes, I mean, because it's a very small quantity. So whatever remains is flat. So it seems that there is nothing there, but I mean, like as with any large like if whenever you take a large parameter to be large in a problem, you need to properly fix also other things. Like you need to be able to look at the right regime of so that non-trivial you can see non-trivial physics, and that non-trivial region is, if you consider psi minus 1 to be order 1 by d. So, and in that region you can see that, I mean, since psi minus 1 is order than 1, so I can write it as 1 plus say something by r d, and here psi to the power minus d minus 3 becomes e to the power minus r plus some order 1 by d variations. So, you can see that in this region, which is order 1 by d outside this horizon at psi at r equal to r naught or psi equal to 1, the space time has a non-trivial profile, and outside this, I mean, as I said, if psi minus 1 is order 1, the space time becomes flat. So, these are all trivial things here for now. So, but the interesting point is that, so you can think of, suppose since I said that I have a slightly undulating membrane. So, these are the two regions. So, there is a black hole region here, there is a asymptotic flat region here, and the region of, like, this is black hole means, I mean, inside region, say inside horizon region, and this is the non-trivial region in space time just outside this horizon, which is non-trivially warped by, I mean, like non-trivially warped in this space time. And this is the large D thing that happens. I mean, like all dynamics can be confined in this region, and hence you can talk of the dynamics of the black hole in terms of talking about the dynamics of the horizon and nothing, more or less nothing else.
One thing I think I did follow. How is psi getting time dependency from your definition?
Psi is getting time dependent because I didn't specify what derivatives I am taking. I can be any derivatives.
Psi is an arbitrary function of space.
So now to do any computation, I mean, I find it easier. I mean, like
The psi equal to r over r naught is to begin.
yeah, then you can convert it to any function. And the way we find that it's easier to solve this problem is to go to a coordinate system. Since all physics is confined more or less here, so you need to, I mean, like somehow do non-trivial stuff only here. Outside it is flat, so you don't want to disturb that. So just go to a non-trivial coordinate system here.
I forgot this, but this large D method, what does it say about the inside the horizon?
So the solution that I consider, I will be mostly concerned with things that happen outside the black hole. Okay, and I will not be telling you much about what perhaps happens inside the black hole.
Yeah, it's completely out of control inside.
Yeah.
But you can control the outside well enough to know that the event horizon is in this transition region. And so for the evolution of the outside, you look. Something similar was true of fluid gravity.
Yeah.
Fluid gravity metric was weighted by r times derivative.
Right.
Derivative by it. So when r became, as you went inside, derivative becomes order r at some point. And then the fluid gravity expansions are with it.
Yeah.
But you don't care because it can't affect you. Okay.
Is it? So yeah.
People do numerical simulations of GR, including black holes, they cut off their metric once they share the inside. It's the same thing.
Yeah, they even don't even find even
They
they find
don't care.
yeah, they only find this what is apparent horizons. Yes.
So some regularity at the, so in fluid gravity when you solve the iterative equation, so you just needed to impose some regularity at the horizon, and that was
That's what we will do here also, because you see to start with the coordinate system is regular at horizon.
Yeah.
So you
What is
don't want to
important to
disturb.
know is that you're going far enough to capture the horizon. Because had the horizon wandered into that inside region where you couldn't control it, then it would be not self-consistent. Because the part you could control would causally affect the part you were interested in. So it's very important that you are able to demonstrate that that cannot happen.
Yeah, and that can more or less be demonstrated by just writing it. Yes. So yeah, so this is the point. Yeah, yeah. Again, please ask question whenever you feel. Maybe I'm not being clear. Yeah.
You don't have to say it.
Yeah, I know. I mean, like it just that's what usually is. Yeah. So yeah, the point is since I think I convinced you more or less that all the physics is confined in this region, which I, for some reason, which I'll tell that I will start calling from now the membrane region. Please remember this, that I call this the membrane region, and so the point is that I will base a coordinate system, and like so I can just choose any point arbitrarily in this region, and say this point is called x naught. So let me go to a different coordinate system based around this point, which I write like this. Say x mu is x mu naught plus say 1 by d y mu. So you can draw a box, okay, and the size of the box is 1 by d, and this is a coordinate y mu is just coordinate system in this box, but since I have like taken out the size of the system here, this y mu system can have infinite extent. Yeah. And now the one thing to notice is that I mean like all derivatives which were like this so the y derivatives become 1 by d times the del x derivatives, and hence when I said that these functions are order 1 derivatives of space time, so looked in terms of this y coordinate, derivatives become order 1 by d. So this is I started doing it like this, but I think this must have been motivated by fluid gravity, because where arbitrary slow parameters are introduced to start with and then taken away at the end, but here it's different. So now what you can do is, since I only need this much, so let me write. So this is the metric that we started with. I will only keep this as like a schematic form for now. Yeah. And so now what you can do is like, so let me write slow varying functions in terms of this y coordinate. So the psi coordinate can be, since psi was based around 1, because 1 was the horizon. So let me start. So it can be written as del mu psi at x naught in terms of y mu times 1 by d plus 1 by d square del nu psi at x naught y nu and so on. Similarly for u mu, you can write a function which was u mu 0 plus 1 by d del nu u mu at x naught y nu plus 1 by d square del nu del alpha u mu and so on. So now the point is that if you put your initial answer solution, which I say was slowly varying functions, and before doing this, suppose you just assume that this was slowly varying function, you put your this answers metric in your Einstein equation, you will find that this answers metric like solves for the Einstein equation to leading order. On leading order, you can see that Einstein equation will evaluate to something that is order d square, because you see there are d's here, and the maximum order of d that the Einstein equation can take out is when both derivatives act on this phi function, and I am saying that this order d square equation in the global x coordinates will be solved if you have something, and what are these conditions? These are simply saying that, I mean, like, obviously you know what these conditions are, these are some equations on you, but the basic point is that this condition is also satisfied by the initial Schwarzschild metric that I wrote. Okay, so locally, I mean, like when you are, I mean, like since you are starting from this point, so locally at the first order inaccuracy, so well, these local patches look like Schwarzschild. That's what this equation also say in a weird way, because these equations are also true for Schwarzschild. But that's true for local. I mean, this once you've done this, I mean, like the Einstein equation, if it is called, it is 0 to leading order. Suppose it was Einstein equation. For now, there is no matter. It's only vacuum that I am studying. But once even you go beyond that order, I mean, and you are in y mu coordinates now. So the thing to remember is that all derivatives in the y mu coordinates just are 1 by d, I mean, like compared to the del x mu coordinates. So whenever I said that initially it was order d square, so there were two derivatives with respect to x mu coordinates. So in terms of y mu coordinates, the Einstein equation to leading order turned out to be something like order 1, because two derivatives 1 by d square were taken out, and hence to leading order it solves. Is it clear? No, I guess.
Maybe I can say a little the same thing, just a bit more physically, which is that while the shape of the membrane varies on scale 1, the metric in the normal direction to the membrane varies on scale 1 by 2, as you pointed out. So Einstein equations are two derivative, and therefore we'll evaluate to something order d squared. But the order d squared is just from this part.
Yeah, order d square is because the metric has a d and not
the normal variation.
Yeah.
Because the thing varies in the normal direction this way. On this way it varies order 1. So
yeah.
And then he's scaling out that order d squared.
Yeah. So I'm just basically just scaling out some whenever. So as you can see in this initial coordinates, it looked like that the initial Einstein metric will bring out order d's. But as I told you, that suppose you chose one of these y mu coordinates along the normal direction.
So for instance, r is one.
Exactly. Yeah. So y, suppose r is one of the y mu coordinates, and in terms of this, you can see that whatever was had to the minus d minus 3 become e to the power minus r, and when whatever had order d square, order d derivatives become order 1 derivatives.
Yes.
So I just slowed down the process.
Normal direction varies on order 1. Everything in the tangent transverse directions varies order 1.
Yeah.
I mean, over length scale.
Yeah.
So you made it like a brain.
Yeah. So yeah, so it's easier to keep track. Just that. I mean, like if you had always can see an epsilon everywhere, it's easier to keep track. So then that's all. I mean, the order 1, it's yeah. So.
It's a bit like the Fermi surface.
Like the Fermi
You know, so it's like it goes as k square in this direction, but goes as relativistic of this direction.
That's a little exactly. So the point is that now, black holes were spheres or whatever they were. But locally, the planes. Because this is separation of scales. The relative length scale of dynamics is 1 by d. And on the scale 1 by d, everything is a plane. That's somehow.
Yes. And if you want to see equations in terms of equations,
That
then
was your thinking also for fluid gravity.
Exactly. So this is very much like
yeah, this one.
fluid gravity prime.
Yeah, I will tell you where the difference comes. So the point is, yeah, if you think about in terms of equations, so to leading order, as I told you, when the leading derivatives become order 1, so Einstein equation leading order is solved provided you input these conditions. These equations have some meaning. I will tell you what. And
So just to say, so right now your the asymptotic region, the zeroth order region was flat space.
yes, still not.
That's why but eventually when you take TMU and backreactions, etc., the asymptotic region will not
Be flat.
Flat space.
Yes, it will be some solution of Einstein equation.
And then all these Taylor expansions that you're doing here, that will have to have covariant derivatives.
No, Taylor expansion you can do in terms of this, but you can just express the answer in terms of covariant derivatives.
The ordinary derivatives will not be nice when you have the asymptotic region as something non-flat.
No, I'm just saying that you can anyway expand it in terms of Taylor expansion, but you can express the final answer in terms of covariant derivatives.
Ah, yes, I see. Well, if you are taking the
Yeah.
it will be lower order. I see.
So yeah, so this is what. Now the point is that that's good. I mean, like it's initial, just the leading order. What if I put this function instead?
Yeah, if you did the Taylor expansion in Riemann normal coordinates,
Yes.
then these are the same.
You're taking away this.
Okay.
Yeah. So the point, yeah. So this is just a demonstration of how I will do the other thing also. Yes. So the point is that now you put this in Einstein equation. So leading order it solves. Now at subleading order you need an Einstein equation at this order. So what can it be functions of? So it can, I mean, like because you can see, I mean, like, sorry. What can be functions of? So it can be functions of this because the Einstein equation had this O mu which has n mu, so you can infer from this that the initial to leading order it can be functions of derivatives of n at x naught, derivatives of u at x naught, because I mean like whenever you take derivatives on these functions in this metric, they will come I mean like with 1 by d, because whenever you take y derivative comes out to 1 by d and here also. And so at this order but it becomes function of ultra local functions of this Taylor expansion coefficients only and not like some other things. And then it can be functions of R. Why? Because as I told you this thing becomes e to the power minus r. So r derivatives when acts on this can bring out functions of r. So now this is the thing like this is the thing where I should say this is the large D magic. Because why? Because initial I mean like so you now the magic because Einstein equations are or let me say one more line before saying the magic. Yes. So now you see it's a function of only r coordinates. It's a non-trivial function of only one coordinate, the r, which r was defined as along the normal directions. This r was one of the y mu coordinates. I have not chosen the other y mu coordinates. And some numbers which are contains data about how the shape varies locally and how the velocity varies locally. So now obviously it doesn't solve, but we can add corrections to the Einstein equation, I mean to the initial metric now. So say I add a correction here, correction metric, but what this form of the Einstein equation tells you is that the correction metric need not be in general functions of all coordinates, all the y coordinates, because the thing that was off from solving the Einstein equation was only a non-trivial function of this r coordinate. So why not just put it as functions of r coordinate only. Now this is the magic, because Einstein equations are
and local derivative.
yes, and but those are numbers, like yeah, those are local values of the derivative. So these are just parameters specifying local. So yeah.
The numbers in the solving procedure, but in the end there will be functions on the membrane. The functions.
Yeah, but at this order, yeah, they are just numbers. So now, if you just put this all together in the Einstein equation now, the Einstein equation becomes something like let me call this 1 because it comes at first order. Del n at x naught, del u at x naught, and r is equal to 0. This is a linear, like ordinary differential operator in r coordinates. But Einstein equations are typically coupled nonlinear partial differential equations, I mean, for which there is no, I mean, like algorithmic method to solve. I mean, but these are, first of all, these are simple ordinary differential equations which you can solve, and it turns out that the ordinary differential equation that we have can be exactly solved, like to give you analytic expressions for the metric corrections. Now this is what is there any question here?
It will be exactly solved for arbitrary.
Yes, yeah, because it's only a function of r. Yeah. So it can be solved, and the
Second order differential equation, so integration.
yes.
How are they?
Yeah, I'm going to tell you now. Yes. So now, so this can be solved, but as Gautam pointed out, there are some ambiguities in the solution. So how do you fix the ambiguities? So first of all, I started with a coordinate system that was regular at the horizon. So I do not want my corrections to do something weird. So I demand that my corrections are also regular, like just metric corrections are also regular at the horizon. So that's one at in membrane region. Secondly, just outside the membrane region, the space-time was already flat. It solved the Einstein equation. I do not want to disturb that. So I demand that all h mu nu in the R goes to infinity, which is does now define the membrane region, because as you remember, it was a patch with size 1 by d around x naught, but the y coordinates had infinite extent, and one of the y coordinates was this thing. So as you reach R goes to infinity, you are just going outside the membrane region. So they demand.
R goes to infinity, but less of an infinity than
Yes.
that.
Yeah.
would be
Yeah. Parametrical. Yeah. So you don't.
is ensured by the
Yeah.
one over t.
Yes. Exactly. Yeah. And thirdly, the point is that there were some ambiguity in definition of this metric. For example, I could have added some 1 by d square correction to the psi, or I mean, like how I define the shape and velocity. I didn't say. I mean, like I could have corrected the shape at 1 by d square. I wouldn't have seen it at leading order. Similarly, I could have had a different definition of u mu, and I wouldn't have seen it leading order. For example, this under this transformations. So the leading order metric would have been invariant. So you can fix this definition. You can make a frame choice of like what your shape and velocity function really are. And one way to do is that initially psi equal to 1 surface was the horizon. So we demand that it remains horizon. Or rather we can say that psi equal to 1 surface remains a null surface in the full space-time. Second condition is that if you look at this metric and you evaluate it at psi equal to 1, the metric becomes something like a ds square, say asymp plus O mu O nu. And you can show that the generator of the event horizon, which is n mu raised with respect to the full metric, like this full metric n mu raised, at psi equal to 1 with respect to ds square becomes u mu with respect to ds square asymptotic at psi equal to 1, only for this much. So basically it says that the generator of the event horizon, which is the normal vector at the event horizon, is actually the velocity field of the membrane raised with respect to the asymptotic space-time. So this is another condition. I mean, like since there was ambiguity in definition, so you want to keep that. Let's keep that also fixed. That we want u mu to still be the generator of event horizon. So if you have ensured all this, there will be no ambiguity left in your problem.
So in fluid gravity, there was this condition that u mu was an eigenvector of t mu.
Yes.
Exactly.
I forget the name of that.
Landau.
Landau.
Yeah.
Landau wave.
Yeah.
Frame. Frame. Right. So is this that kind of fixing?
That's exactly the
definition?
exactly the As again in fluid gravity, you have the freedom to make field redefinitions of u and t.
Yes.
And that will formally change your metric, though it's trivial. So
Like u and psi.
like u and psi. It's exactly the analog of that. Here, of course, we had to find a frame choice that was more naturally adapted to the problem. That is a beautiful one, which is that psi is the event horizon, psi equals 1 is the event horizon, and u's are the generators. So it gives a very clear geometrical interpretation.
I see. So this complicated UT equation, the n mu equal to e mu, that sort of stuff, that ensures that u mu is a generator of
U mu are the generators. U mu as a vector field is a generator.
So
That's it.
yeah, because this side is the generator of the event horizon. Is the n mu.
You take the normal vector, raise it here.
Sorry. So now, since we are talking about fluid gravity a lot. So let's look at one more thing. So it looks like that. This looks like exactly like fluid gravity, but
So just one
yeah.
more comment. These are exactly these Raychaudhuri geodesics.
Yeah.
The thing for which Raychaudhuri's equation.
Yes.
Yeah, so I mean, it's very natural structure that has been studied for so many years. And those guys, the way that.
Yes.
Yeah. This is true to all orders.
Yeah, we want to make sure that it is true to all orders. I mean, you cannot be sure from the start.
You can always ensure that it's true. Because in leading order it is. It's leading order could have been violated at first order, but then you choose your integration constant.
So that it sets it.
There's exactly as much ambiguity.
Yeah,
Just a field reduction.
yeah, because the initial problem had the ambiguity. So, yeah. So yeah. So now, since we're talking about fluid gravity, so there is one slight difference between fluid gravity and this. So this also looks like derivative expansion because it was everything is slow in this patch coordinates and we are expanding in that. There is one piece of it. So I didn't tell you is that whenever we want to ensure the problem maintains a SO d minus p minus 3 isometry when d goes to infinity and p is finite but arbitrary. So you can, for example, one example of this thing is that suppose you consider this metric, like, and it's an example like dt square plus dr square plus r square d omega square. So this has a huge, I suppose this is d minus 2. So this is an extremum. So this metric has a very large isometry in this system. Now, the one of properties of this matrix is that, I mean, suppose you want to take a divergence of a order 1 vector. Like every vector in our problem is order 1, its derivative is also order 1. But the divergence becomes del mu a mu plus gamma mu theta a theta. But you can easily tell that this gamma mu theta has a component, I mean, like one of the gammas that can be contributing here is gamma. Suppose I call this sphere coordinates ij coordinates. So ij theta, and suppose this theta, suppose this is r coordinate. It is actually 1 by r delta ij. So when you have a huge isometry, suppose it will have a spherical part like this, and whenever you sum over these gamma mu's, you can easily see that this part actually becomes to leading order d by r a r. So you can see even though the derivatives are order 1, which I assumed, there is a part coming from the Christoffel symbol which is order d. So naively all derivatives are not order 1. So whenever you take divergences in situations which preserve this SOD minus P minus isometry, there can be terms which actually go on to compute at higher order. So this is the only difference between this and fluid gravity.
So P will come if you put some P number of flat
Yes,
directions in
Yeah.
this matrix.
Yes, you can just add ds square plus dxi and write this as h square and so on. So then it will be along the, like,
And the sphere will be D minus P minus 2.
yes, exactly. But this is the point that whenever you have a large isometry, you have a part like this, and this will contribute a Christoffel symbol like this, and naive derivatives, at least in the covariant, I mean, like in divergences, that notion gets, I mean, like a bit changed.
And the horizon is not allowed to wiggle in the x, this xi, I mean in the spectator direction. So they are just
Yeah, because I have mentioned that it preserves the SOD minus.
So it is a lot very.
Spectator directions means?
meaning that you know you are just extending whatever solutions you add in P mode directions.
Yeah, it's not, the horizon is not allowed to wiggle in these directions. Yeah.
But it can wiggle in the x axis.
Yes, it can wiggle in everything else. Yeah.
But then your SO D minus P minus 3.
Isometry, it will be preserved, right?
Oh, I see. That is why it becomes D minus P minus.
Yes.
Because it also wiggles
In any everything else.
So you can wiggle in any finite number of directions. You should wiggle all together. That's all.
So, yeah.
And actually, it's possible to rotate this SOD minus P minus 3 into different.
Yes.
This condition is, while sufficient, is too strong.
locally.
Powers of the elements.
Yes.
And there are configurations that don't preserve the whole isometry, that maintain these powers, and everything we do is correct.
Okay. So yeah, this is the. So the point is we started with a ansatz metric, which initially every patch looks like Schwarzschild, and it solved vacuum Einstein equation. Then I made this function psi and u slowly varying functions. To do the computations, I moved to a local patch, like this patch coordinates, and then I showed that the problem can be converted in terms of ordinary differential equation in the normal direction, and you can always solve these equations, and these are how you remove the ambiguities, and then you have a Einstein solution to a black hole, dynamical black hole solutions to the Einstein equation at order 1/d. Obviously, from the way it has been done, you can easily see it can be taken to any arbitrary order. I mean, like at least in principle, you can take it to any arbitrary order. Oh, by the way, one more thing I didn't say. So it's all well and good that you get solutions like this, but there is a one obstruction to the solution of Einstein equations, and that obstruction, like you just cannot start with any initial data, like any initial value of the shape and velocity function, and land up with a black hole solution. There is some obstruction, and the obstruction comes about in terms of this equation. To say the first line, it's simply a constraint on the shape and velocity function, and once you start with shape and velocity function which satisfy this condition, you can land up with a first order corrected solution of Einstein equation. And if you want to know what these are, so this is simply the velocity field of the membrane that I started with. This kappa kBa is the extrinsic curvature of the surface. Extrinsic curvatures are simply the way the normal unit normal on the surface moves along the surface, and these covariant derivatives are all with respect to the induced metric on the membrane, as the membrane is embedded in the asymptotic spacetime, and this projector is orthogonal to the u direction in the induced spacetime. So, and there is one more equation which to leading order, I mean this will not come at leading order. Okay, I just this is way of writing it, just simply say that I will tell you what, but to leading order it simply comes out to be order is 0. So there are two things to say. First of all, I told you that u so u was the generator of the event horizon. So to leading order, this being 0 simply says that to leading order generator of the event horizon is like, I mean, like it's like entropy current, right? So to leading order simply says that there is no entropy production in the system, like the system to leading order is not dissipative.
You wanted to impose these equations so that there is no mixing of orders, so that you want to
No. I mean,
or why?
so there are two ways to see it. First of all, I mean, you will see that even after you have solved this Einstein equation, some components of Einstein equation even unsolved, and you need to put these conditions. Those components actually turn out to be the constraint Einstein equations, and I mean, it just accidentally it turns out to be the constraint Einstein equations, and you can think of it as you have not set up your initial data properly. If you don't satisfy this condition, then you just simply say that you have not set up your initial data properly. So these are the constraints that you need to put on your initial membrane data, so that you have a regular solution of Einstein equation. And sorry, please ask again.
So you have the second order differential equation.
Yes, a set of second order differential equation.
Second order differential equation.
Yeah.
So these are all dynamic. These all basically came from the dynamic part of the Einstein equation.
Yes. Yes.
Although this is second derivative in time as well.
No, it's ordinary second. Yeah, it's R coded. It's ordinary second. All time derivatives are encoded in this Taylor expansion
So
coefficients.
now you are saying that, however, in the initial value problem in time,
in R.
In R.
Yeah.
Okay, I see.
Yeah.
Oh yeah, I see.
Yeah.
Okay, good.
Yeah.
So in R there will be a constant like equations.
Yeah.
And these are those.
Yeah, I mean, if you demand that your metric is regular in the constant value equation, you need to impose these two conditions.
Yeah, basically yes.
Yeah. 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 So that's what I say. Once, if you have imposed regularity, then you will see that some of your equations are not solved, and you need to put these constants by hand to.
You have to put these conditions anyway because you're doing a radial ADN.
Yeah, but yeah, okay, yes. I mean, but you can also naively not do it, and then at the end find that you need to impose these conditions. Yeah, yeah.
Okay.
Yeah. So the first point of these two equations is to see that this says that there is no entropy production at leading order, and second point is that you can count the number of equations. So as I said, this is I mean, think of this equation as being in induced spacetime. So it has one less dimensions already, and then there is one more projector orthogonal to the u directions. So number of equations here is d minus 2, because once you go to induce and then you take out another direction in this, and number of equations here is 1. So total number of equations is d minus 1, and your initial variables were psi function, which is one scalar function, and u velocity function, but it has two constraints, that u dot n equal to 0 and u dot u equal to minus 1. So it had also, so there are d minus 2 plus 1 variables. So there are d minus 1 equations for d minus 1 variables, but that mostly doesn't say anything. I mean, like doesn't say much about if these equations are really dynamical or not. But you can solve a simple problem of yeah, you can solve a much very. I mean, there's something, the number of equations, number of variable match, but that doesn't say much. But you can solve a set up a very simple problem where you study, suppose a very simple dynamical situation. This initial condition, as I said, was the Schwarzschild black hole, and yes, I mean, epsilon is not 1 upon d. It's just some amplitude perturbations over there. You can okay, yeah, amplitude perturbations about this, and you can put these equations in this this thing and this, and find the spectrum of these fluctuations. And I'm not going to tell you the spectrum, but I'm not going to tell you the profile of this function, but what I can tell you is that the linearized spectrum, the frequency of the linearized spectrum has a form like this. So now these thetas are the full sphere in Schwarzschild, and these L's are the spherical direction, the angular momentum numbers of the spherical direction in Schwarzschild. So this simply says that the spectrum of, the best part is the spectrum, this comes out to be the spectrum of this fluctuation in this equation, this membrane equation. And amazingly, this actually matches with the quasi-normal mode computation in gravity in large T, done by Emperor and Suzuki and Tanabe. Basically, this matches with the long-lived modes there. There are some modes which die off very fast, but this actually captured the long-lived modes. So basically, you can think of this. So there are two things. First, it does say that in a very simplistic situation, it does capture the dynamics of the gravitational fluctuations in black holes, and secondly, it says that it matches with the that thing, and what more? Yeah, and secondly, yeah, it just says that basically, and secondly says that they actually capture the late time dynamics of a black hole in a dynamic process of a black holes.
Yeah. Thirdly, it says that at least in small fluctuations around the black hole, it's a well-posed equation.
Yeah, so that definitely says yes. Yeah, but yeah, will be done.
So L equal to 1 mode does not damp out, or
Yeah. So since you asked, okay. So there are two L equal to 1 mode. First of all, this is a velocity mode, so let's keep it aside. So even there are some more problems with this here. So even the L equal to 0 mode, you will see has a problem. Okay. Yeah. So L equal to 0 mode, even if so it has one growing and one 0 value. Or I think I made the other sign. Whatever. Yeah. So there are two problems. So first of all, in the L equal to 0 mode, this mode you can see that it's a false mode. I mean, like just you can put this in one of the other equations to show that it's a false mode. And this mode, which accurately says that it's a 0 mode, it's the right 0 mode for the rescaling of black hole to happen. I mean, that rescaled black hole is a solution of Einstein equation.
What does it mean by false mode?
False mode is, I mean, like you can just put this equation back into these two solutions and you say that it will not solve.
Yeah, it means that this is the correct spectrum except for that mode at n equals 0.
Yeah.
These are not really solutions.
Yeah.
Okay. You've made some assumption in solving which is not true.
Yeah.
While solving, we have assumed that 8 is not equal to 0.
Yeah. Yeah.
So there was an L equal to 1 part of the corrective coordinate itself.
Yeah, that. Yeah, that is. First, this is okay, right? That L equal to 0 is the rescaling of the black hole. This is fine, right? Yeah, that has to be a solution. So it's a constant solution. This second, the L equal to 1 here. So L equal to 1 here can be thought of as like a boosted black hole, and a translated black hole are also solutions. Scalar mode, scalar L equal to 1. Say scalar L equal to 1 is proportional to one coordinate.
So translation is a vector,
Yeah.
and vector is n equals 1. Vector boosts both are angular 1 to 1. So the solutions, as he said, there are two solutions at n equals 1, and you get a solution and then a log. And the log is the boosted solution. It's the motion.
And this L equal to 1 is most probably you have already guessed. This is just simply small rotations. Yes. Yeah. So this is also solution. Yeah. So this.
So vector spherical harmonic at n equals 1 gives you the adjoint representation, and rotations give the adjoint representation.
Yes.
So all the funny modes are all physical. Everything that's not funny behaves.
Yeah, you can see funny part was also there in the gravity thing, but it's not something we found out. Yes. So now going beyond, I will first I will speed up, yes, and going beyond, as you can see, I mean like I think I can. Oh, sorry, this is not very useful. So I had some Taylor series expansion of each function, right? I mean, like for example, let's take the u function. It was u mu 0 plus del mu u nu at x naught plus double derivative u at x naught and so on. So now you can see that you can easily extend this procedure, like in this full thing, once you have solved for the h mu nu, and go to one higher order. The procedure doesn't change because now the Einstein equation will be functions of single derivatives of n, single derivatives of u, double derivatives of n, double derivatives of u, and r coordinates at 0, because it is at order 1 by d square. So you can as well add one more correction, 1 by d square. That also needs to be a function of r. I mean, like blah blah, and you can solve for the metric corrections. So you can see it's a systematic procedure that you can use. But obviously, you will again find an obstruction to solving this equation, because again you have not set the initial condition properly, and the obstruction comes in terms of some corrections to these equations. Okay. So I have written only few terms in these corrections, just to say that it can just take up the whole board, the number of corrections at this order that I have to write. So this is the correction to the vector part. Don't look at this, I will talk about this later. And this is the correction to the divergence of u part. Now if you recall, u was the generator of the event horizon. This equation to leading order said there was no entropy production. So this equation at this order says there is entropy production. In what way? You can just integrate this equation in some slice. It will just tell you the del T of S And since there is no, let me assume that I close the manifold, there is no boundary term, and you will find that this is the rate of entropy production, total entropy production. And this is positive definite because it comes as a square, and in large D, kappa turns out to be positive. So this simply says that second law is not violated. I mean, like, we didn't put in second law by hand, it just comes out, and this comes out like this.
So kappa being positive, of course, when there is no p equal, there is no brain business. Then of course is some spherical stuff, and kappa is the extrinsic curvature scalar, so of course it has to be positive. And now I have a gain here, and then the extrinsic curvature can go back and forth between positive and negative. So, but even then,
Yeah, that's why I say it's
curvature scalar is
too large D's. As I told you, I mean, like, any divergence.
Oh, I see.
Yeah.
So you've got the sphere, which has order d coordinates. That is always positive. This is some order 1
I see.
perturbation.
Yeah. Exactly.
But for black brains, it don't hold.
What? Well, if the black brains also have a p sphere, it will, a d sphere, it will.
Yeah.
So what Emperor calls a black brain, it will.
Because P is order 1 and D can't.
Yeah.
Where this derivation is valid.
So that works.
By the way, so I had just one comment about P equal to 1. So you probably have some large D description of Gregory Laflamme, right? So maybe you guys have already studied this, right?
Yeah, we wrote a, yeah, imperant wrote, and we just show that our things also gives the same thing. Yeah.
It's a very interesting story about that.
Yeah.
Later.
Yes.
Emperor has written a beautiful new paper, as you probably I mean, new meaning to think.
Oh yes, that one. Yes. Yeah.
About this, which is quite remarkable.
So now this is old stuff, and the new stuff will take very little time once this is all set up. So now, what I wanted to study is actually a different thing. As I told you, I wanted to study solutions of okay. So
Now, this d mu is what? It's something fixed.
yeah, that will tell. Yeah. So now, first of all, let's look at this part. Okay, like how do I? What do I mean by this? First of all, you saw that just let me write the metric again. Yeah. This was the answers metric. To leading order, what I am now demanding is that, I mean, like, let's start with this answers metric. So in the d goes to infinity limit, outside the psi, much outside psi equal to 1, this spacetime still goes to d square asymptote. Earlier I assumed that the d square asymptote was flat because it was solution of vacuum Einstein equation. Now I am assuming that the asymptote flat is not flat but a solution of this equation. Okay. So now how do I make, well, like, put it into the computation? So what I need to take care of is the parameterization of this only in the region where I need to solve for the Einstein equation. With the, again, as
But does d mu respond to the change in the metric? What is it? Roughly, what is it?
yeah, so T mu nu is yes, T mu nu is some fixed, like, given thing.
But what does it mean that it's given? As metric changes, what does it mean that tensors?
What is the mean by tensor given means?
Meaning in which coordinates? To say that T mu nu in a given manifold is given makes sense.
Mm-hmm.
But now we're going to be looking at different manifolds. Right, as the black hole ripples around, it's a new manifold.
Yes.
So what does it mean that you've once and for all specified?
So I think after the order that I will be interested in, it will be the value of the local value of the T mu nu only at that point that will come about in the equations.
So it will only be the T mu nu in flat space.
Yes.
That will matter. And as this thing ripples around,
Yeah.
it doesn't change this T mu nu. Suppose it was a scalar field making.
No, for example, I mean, like, it does matter because the T mu nu on this side has to be conserved to be.
It has to be conserved, but it might ripple around in other ways as well, right? Suppose there was a scalar field
Yeah.
for a moment.
Yeah.
Oh, suppose there was a Maxwell field.
Yes.
This is the case we've got.
Yes.
So then you not only, it's not enough just to say that there's a TB nu, you have to solve the equation of motion of that other thing.
In the presence of gravity, you mean?
Yeah, you have to solve the couple Einstein Maxwell equations, right? That's
Yeah.
sort of way of proceeding.
Conservation is not enough. Del mu T mu nu equal to 0 is not enough, right?
What does del mu T mu nu equal to 0 give from Maxwell?
But Maxwell's equations imply del mu T mu nu equals 0,
Huh.
but are not implied by it. Right?
So-
you can use Maxwell's equations to show del mu T mu nu.
So,
You can't use del mu T mu nu equals 0 to cover Maxwell's equations.
so I will only use that it's
Conserved.
conserved.
So
Yes.
that's very interesting. So in particular, you're saying that some of the part that we did for the Maxwell calculation could have been done using only its stress tensor.
Most probably. So, yes.
Okay.
Yes,
Please
yeah,
proceed.
yeah.
Sounds interesting.
Yeah. So, as I said, I will only be interested in how the metric looks here, because I am solving in the membrane region again. I mean, like now, suppose this is black hole, this is asymptote. So, you can again start with the procedure again, like, and now there will be a suppose how will I parameterize the asymptotic spacetime, asymptotic spacetime part of this full black hole, full metric. So, what I am saying is that I will be demanding that the curvatures of this asymptotic spacetime are order d naught or order 1 and you can parameterize the metric in the asymptotic part in terms of as you were saying the Riemann normal coordinates. So, in that coordinate the metric,
Now I'll be back in 2 minutes. Please continue.
yeah. Let me say epsilon is 1 by d. Say some number #1 which can contain derivatives also.
You mean epsilon cube there.
Square, oh sorry, cube. So, the point of using Riemann normal coordinate, as you know, is that it's just one of the normal coordinates where there is no Christoffel symbol. I mean, like, so I mean, like, just getting rid of the Christoffel symbol locally, and these are also values of curvatures at this point and derivative of value of curvature at this point.
Okay, just the second point, I think G mu nu times T mu nu is something that you want to hold.
That's true.
So that they will factor.
Yes. Okay. Now,
Is this the solution? What is this? This is the
this is just one way of parameterizing metric locally around at any point. Yeah. I am not yet solved for anything. So, it's that like I was parameterizing shape and velocity as slow functions, I have also parameterized metrics as slow function, and as you saw, these things had curvature order 1, but order 1 curvature will be like order d square 1 by d square curvature in the y coordinates, because there was 1 by d shift between y and x derivatives, and so on. So, now you can so now what you can so also now T mu nu,
Sorry, just one second.
Yeah.
So G mu nu will have both
Yeah, these are all. The y coordinates I didn't specify. This can have anything.
But hold on. So the derivative counting
Wait, just a
along
minute.
radial and along this thing.
Yeah.
Sorry. So why is there a radial like delta r square terms also have epsilon square?
Yeah, but
Oh yeah. I guess. Got it.
yeah, this part is just smooth order 1 part. This part contains all the d derivatives.
Yeah. Your box has size already both in radial
Huh.
directions and.
Yeah. All the weird things comes because of this, not anything else in sitting in. Yeah.
Previously it was intermediate, now you are choosing something else.
Yes. Previously it was just intermediate. Now I am choosing that it can have some curvature, but I can defer the curvature to order epsilon square. Yeah. Locally, because I am only probing locally. Huh?
So the change is due to the T mu.
Even without T mu it can do. I will just tell you because the vacuum Einstein equation can have non-flat solutions. Yeah. So now also T mu nu. Suppose there was this definition between x so the T mu nu in the x coordinates which sits in this equation is actually epsilon square times the T mu nu in the y mu coordinate, because you can see that this is actually del, how does it go? Wait. Sorry. So T mu nu in the y coordinates is del x alpha del y mu del x beta del y nu times T alpha beta in the x coordinates. So this simply comes out to epsilon square T alpha beta in the x coordinates. So now you just evaluate. I mean, like first of all, I need to actually find these solutions now. Like or parameterize these solutions first before going into the black hole part, because the black hole outside the membrane must go to a solution of Einstein equation. So you need to just put this together in this Einstein equation. As you can see, the curvature will be starting at order epsilon square in this Einstein equation, and to balance it, I have found a stress tensor which is also order epsilon square.
And you need this epsilon cube term also?
Yeah, that's what I am saying. I need this epsilon cube. In fact, I need many other terms. I mean, it can go on like this, but the point is when you evaluate the left hand side, putting in this thing. So the issue comes because divergences can bring order d's. Okay, so this can always rise one higher order. More and more, you can have divergence can go here. So the point is, but the interesting thing is that Einstein equation is also two derivative. So whenever a divergence actually from here goes here, it comes with one free y index. Okay, but now you can also do a Taylor expansion of the y, but the y coordinate, since it started at epsilon square, it cannot have any Taylor expansion. It is the value of that stress tensor at that point. So you on one hand you will have something.
So your T mu nu was already d to the 0. Whatever its trace was, that also d to the 0.
T mu nu trace. T mu nu trace is ordered d to the 0 because I am maintaining SO d minus p minus 3.
But you could have had a trace maintaining.
Yeah, I guess it doesn't matter. The trace need not be ordered d to the power 0 because, wait a minute, because this r mu nu, this equation can also be written as r mu nu equal to 8 pi g times T mu nu minus T by d minus 2 into g mu nu. So you can also have order, well, you can also have order d traces even. Yeah, somehow they cancel out. Yeah. So you can turn on some uniform thing in the sphere direction.
That's sort of interesting. Now, previously, you might have thought that in the Ricci, for instance,
Yes.
could have been order. The fact that R is order whatever it is, 1 d squared.
R mu nu alpha beta is order 1.
Order 1 your y coordinate.
Yes. No, no. I am talking about this part only. I am writing this part as.
Yes. Ah,
Okay, yeah.
I
Yeah. Yeah. Sorry. Get that again?
Yeah, so I was saying the fact that R mu nu alpha beta was order 1
Yeah.
needn't have implied that you could have had Ricci firms, R mu nu, being order D. Right?
Yes.
Now, normally that won't happen because Einstein equations tell us R mu nu is equal to Z.
Yes.
Now, R mu nu will be related to some T mu nu.
Yes.
And you're saying that that will still be order 1 because
Yeah.
T mu nu is order 1.
Yeah.
But R
Yeah.
could be order D.
Yeah.
Riemann scalar could be order D.
No, but there is one issue with that being happening, because you see, I wrote this G mu nu as a expansion like this. I need to maintain isometry here. So this will prevent certain components of R mu nu alpha beta being there because if I turn on something, Y symmetry, something else will also be turned on.
Yeah.
I cannot do that, and that will, as you can specifically see, will I will have to put R mu I j nu times things to 0.
Okay.
And these are the things that will usually add up to give you order D things, because yeah. But because of this one minute, I can actually do something more here. Yeah. So yes. So now once you once you put this and this together in Einstein equation, you will have something like, let's say, at order epsilon square, you will have R mu nu at, let me use this equation, okay, and let me call this whole thing tau mu nu at x naught is equal to plus some number times divergence of some
Y alpha don't have any coordinate along the angular direction.
yes, because I need to maintain an isometry and some other terms, but this is equal to epsilon square T mu nu. So as you can see, I mean, this cannot be solved because these are both values at some point, and this has a y coordinate, so I better put these things equal to 0. So this is one more condition that I need to impose on my curvatures. Also, you need to put divergence of T alpha beta equal to 0, even though I am not turning on derivatives, because as you saw, divergence brings out extra orders of D because of Christoffel symbol. That is one thing. You need to make sure first in the asymptotic spacetime. So once you have done that, you have parameterized your asymptotic spacetime. Let me just clear some parts out. Which part should I clear? Oh dear. This is the part I need. So you can now solve for the parameterization of this asymptotic spacetime that I wrote, and now you have.
I don't understand. Can you impose that condition that this del alpha r alpha mu beta nu equal to 0?
Yes, I am imposing because I am constructing the solutions.
How can you?
Because I had free, were free parameters, right? I mean, sorry. This is actually Taylor expansion coefficient, because in Riemann normal coordinate this comes as Taylor expansion coefficient. So I am just taking that for consistent solution, you need to put these components to 0.
Either it is 0 or it is not 0. How can you put it to 0?
When you can only study those solutions where this is 0.
Those are background.
Background solutions.
So I also am confused. So those would be very rare conditions. Right?
Those will be very?
You're saying this is a constraint to the background space-time?
Yes.
So it's very very constrained.
Yes.
Okay.
If you remember, the metric was expanded like this, like eta mu nu here and so on. So
Are you saying the fact that the background solves Einstein's equations tells you that?
yes, yeah. Because otherwise it cannot be solved. And some of the terms are independent of coordinates, and there is one thing that is dependent on coordinate, and you can that thing can go anywhere. So you need to put that equal to 0.
You need to put the 0, it comes out. What,
I mean, for example, I mean, if there is this part, I mean, suppose you are doing it in
let's say you have the electromagnetic field case.
yeah.
Then is this equation satisfied or not?
I'm not sure actually.
And there are 3 indices, right, in the next function.
3 indices means
3 indices.
why?
That should be beta, right? If you mention.
Oh yes, sorry.
And then for all arbitrary y beta, if it is true, then it have to be true in 3 indices.
What 3 indices means? Oh, there are 3 free indices. There are 3 equations you mean?
In this equation.
Yes, yes, yes.
And now how many equations?
There are many constraints. Yes. So
I am saying there are too many equations with respect to.
you mean to say there will not be any free thing left after I have solved this? No, most probably. Is it what?
So Einstein equation has ordered d square number of equations. Now this equation seems like it has ordered d cube number of equations.
So let me just go to a coordinate system and write it out. So if you are, suppose this y coordinates in the flat part, where a coordinate system like where the metric, this eta mu nu part can be written as what these conditions will imply that whenever you have a R metric with S component, you set that to 0. So you cannot have things with S components.
Because the divergence is basically S.
Yeah. I think yes. As I told you, the divergences bring out one component, and it's a order course. So this is one thing. Is it okay? Yeah. Yeah. So now, yes. So yes. So now after that is more or less the same procedure. So the interesting thing is that I need not the non-trivial computation that I need to do compared to the previous thing has been deferred to order epsilon square. So to leading order, all the metric corrections and these membrane equations do not change modulo the fact that you change all derivatives by their covariant functions. I mean, this is the property of Riemann normal coordinate, that you can do that because the Christoffel symbols are 0 locally and all the equations are also local. So you take the computation to higher order. So basically now what you end up with, now an Einstein equation, let me call this full thing the Einstein equation now, and let me call it with stress tensor. It will be a function of, again, obviously the shape things, and then the Riemann value of the Riemann curvatures, and modulo this fact that these curvatures solve this equation. there's some questions. So now you can, well, like the rest of the procedure is the same. You add metric corrections. Sorry, obviously this will have a r coordinate now. 10 minutes?
Okay.
10 minutes or 5 minutes?
I think they have that. Is it okay? 3-4 minutes.
Couple of minutes is fine.
Yeah, fine. Yeah. So you solve for the metric corrections. You can, the metric corrections will turn out to in terms of this. And the interesting point is that you can solve for the metric correction. There were two interesting, I think interesting points. First of all, the correction to the membrane equation, one of the membrane equation will turn out to in terms of a term like this. So it will be just picking out the u component of the stress tensor. This will how the membrane is forced. And the rest of the interesting thing is that the rest, I mean, if there is no stress tensor, the membrane simply just adapts itself to move in the new background. I mean, it's not forced by an explicit curvature term. And this.
At next order, there's no curvature.
Yeah, that's it. I mean, no curvature term.
So this is
This is at this order epsilon square.
epsilon square, which is like first subleading.
Yes, yes.
There's no curvature coupling. I didn't know that.
Yeah.
Okay, that's interesting.
Yeah, this also matches with Shantani's and Yogesh's computation.
They also come to this.
Yeah, no curvature.
But there was in the metric, but not in the metric.
Yes, 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 yes. The membrane actually adapts itself to move in the new background. And secondly, the correction to the entropy production is a term like this. So now you can interpret it in two different ways. First of all, in terms of the full background metric, UAs were actually
For Shantani and company and for Schumann, I mean, the TAB was just the delta AB.
TAB was actually delta, but they had some more term because they had some other way of scaling, right? Because they are, yeah, I couldn't actually compare with that answer.
Right.
Yeah, but I could compare that this was.
He had order 1, you had order D square. Order D square. Yeah.
And secondly, the correction to the entropy production term is this. So it thought in terms, yeah, because yeah, it's positive definite because UAs were generator of the event horizon which were null. So if you impose that it has a null energy condition, then it is positive. But it thought in terms of the membranes, these U's are like some time-like vectors. So for the membrane, like this is positive definite if
Strong energy.
it's a strong or whatever weak or strong energy conditions. This is this map. And but then there will be some obstruction to this solution, and that obstruction is because I didn't tell you that I also need to impose grad mu T mu nu equal to 0 in terms of this full. Where did the full thing go? Come on. Yeah, full metric, like it was ds square asympt plus O mu dx mu square by chi to the power d minus 3 plus corrections, first at 1 by d, then at 1 by d square. So you need to impose that the conservation is had, and this conservation is actually converted into this equation that O mu T mu nu equal to 0. So the black hole can only be an environment of a matter stress tensor for which O mu T mu nu is 0 is satisfied locally, and these are the membrane corrections, and you can also find the metric corrections. And so this is just a theory. So I basically constructed, I think I have constructed a black hole solution, but I call this black hole solution because to leading order you see the metric is still eta mu nu. So the leading order, everything looks still like local patches of Schwarzschild. So it's actually a Schwarzschild in a soup. So this is what I think I have constructed a Schwarzschild in a soup solution in large T, and I think this can be the end product of a collapse which forms black hole.
Maybe we can go outside.
Yeah.